It is truly an honor and a pleasure to be able to present to such an esteemed audience. And hopefully, they find it insightful and useful and getting an understanding of what's happening in the nuclear landscape. With that, I'll try and be brief in my presentation. I have not added slides just so it feels more natural, so you don't have to focus on both me and a slide deck or divert your attention. But I will start at a very high level. When we talk about energy, even outside of nuclear, we tend to think of it in terms of three levers. So, what we colloquially call in the energy sphere the energy trilemma. And it hinges on three legs. One is energy availability, the second is energy security, and the third one is energy sustainability. And each one gets balanced against the other in order to make an energy decision or an energy policy decision for a nation, for a state, or for a continent. Now, when I say energy availability, that translates to roughly access to energy. So if you think about how much we consume per capita, in the US, it's roughly about 10 to 11,000 kilowatt hours a year per head. So when you take that into account and you look across other countries, let's say in Europe, that number is about 6 to 7,000. If you go to India, it's about 1,500 kilowatt hours a year. And if you then go to Africa, you're talking about maybe 100 or so, 200, 300 kilowatt hours a year. So you can kind of see that energy availability becomes a big thing. It directly correlates to quality of life, to automations, factories, electrification. So if you think about load growth and energy growth, if you want to increase standards of living, that means that we're going to have a pretty significant growth in energy to get to the quality of life that we have by Western standards or developed nation standards. Now, the question then becomes, where do you get that energy from? Which leads to the question of energy security, the second leg. So energy security means, do you have natural resources? Are you blessed, as is the case with the US, where we have a lot of energy domestically? Um, or do you have a lot of resources such as Norway? They have plenty of hydro, so they're almost self-sufficient in that respect. Or are you dependent from external sources, right? So if you think of island nations such as Japan, they don't have good domestic resources, so they're dependent on imports, right? And that can create different political frictions depending on where they get their energy. So they have to have reliable energy supply or partners. If they don't, that creates a security risk for them. And that leads finally to the third leg of the energy trilemma, which is sustainability, right? So how do you produce your energy? If you produce your energy in a sustainable manner, are you polluting? Does it have knock-on effects globally and locally, right? So it's not just when we talk about emissions, not just your CO2, but also your local pollutants, such as your particulate matter. Also, it creates issues around equity. Land values are typically lower near polluting sites. So you kind of have to factor all of this in a blend and trade between the three stools to then decide what is your optimal mix. So what has happened over the last few years is we've seen a real shift based on these three legs. And we've kind of heard a lot nuclear coming up more and more frequently compared to what it used to. There are obvious reasons why. Ukraine was kind of a turning point, the invasion of Russia into Ukraine, and the cutoff of natural gas supplies to Europe. It created a bunch of changes in energy flows. We became a much bigger exporting country, the US did, with our LNG terminals to Europe. And then it reshifted trade routes for gas and coal. And it also forced a reminder to policymakers of what had happened during the oil embargo in the 70s, which is why a lot of countries in the first place adopted nuclear programs for energy security reasons. So in the US, what has happened, we've seen bipartisan support both at the federal and state level. We've seen significant policy decisions and acts come in supporting nuclear. from the federal level, but also then we've seen at state level reversals of nuclear moratoria. So states that disallow new nuclear builds have reversed those moratoria because they've come to the conclusion that they should have an all of the above mix. We've also seen states come out in full support of nuclear. So Texas is one, Virginia is another. They've included in their energy plans. And more recently, New York. They released a roadmap to nuclear for the state itself. Now, in Europe, we've seen obvious support from the typical pro-nuclear countries such as France, but also we've seen reversals in nuclear phase-out policies. So Sweden and Belgium had phase-out policies. They've scrapped those and decided, hey, we should keep our plants running longer and maybe consider building new nuclear. That has also happened in the UK. But also you see a lot of newcomer countries that are interested in nuclear, such as Poland. Slovakia would like to build more nuclear. They already have some, same as Slovenia. And then finally in Asia, we're seeing the same trend. Korea had a phase-out policy. South Korea had a phase-out policy. They reversed that. And they're including nuclear in their plans, same as Japan. Japan, post-Fukushima, had taken a very slow approach to nuclear, to restarting their industry. They've been very, very careful how they do it with just cause because of their experience, but they've reintegrated nuclear as part of their future energy policy. So we're kind of seeing this shift towards nuclear because of its attributes as an always-on source of power. It has extremely high, what we call in the industry, capacity factors, which means how many days of the year are you available to produce power. It's about 90 to 95%, which is significant when you compare to other sources. Wind is about 40%, solar is about 25 to 30, gas maybe 60%, same as coal. So you can kind of see that the always-on nature is a huge attribute. The other thing that adds to the energy security factor for nuclear is that it manages to have a lot of power produced from very little fuel, which means, and it also has a time delay, right? So the fact that you can burn fuel for 2-3 years at a time, it's just uranium rods. That means you don't need always on-time supply, same as you do for, let's say, natural gas, where if you turn off the spigot, that means your supply is done. So it has a time shift or a time buffer for energy security reasons. So with the policy landscape kind of gone over, I'm going to jump into like, well, what's happening in the market side, on the demand side, right? So we're seeing a huge increase in demand that we hadn't seen before in the electricity sector in the US. Usually for the past 10, 15 years, it was basically no growth or 1% growth in electricity over time, which is not significant enough to warrant significant new investment in infrastructure. But what has happened over the last 3-4 years, we've seen a huge explosion in growth where all utilities have had to start re-baselining their integrated resource plans. Those are their master plans for what they project is going to happen in the next 10 years. So they can start planning capital infrastructure investments. A lot of reasons for that. One is manufacturing. We've had a shift in domesticating manufacturing, onshoring factories. You can think of chip fabs, auto plants, and increasing our domestic supply in general. The other phenomenon that has started happening is electrification. We've talked a lot about how do we electrify industries, talk of onshoring manufacturing, whether that's for chip fabs, auto plants, steel production, just an increase in demand for power and energy for onshoring manufacturing. At the same time, we've heard a lot about electrification. So electrifying mobility, around electric vehicles, electrifying building stock, so moving away from natural gas heating and cooking and going to electric stovetops and electric heating, heat pumps. And then also the aspect of decarbonization, right? So what happens to our industry, right? What happens to refineries? Do they electrify? Do they burn alternate fuels? What happens to our steel producers and aluminum smelters? Do they go electric arc furnaces? Do they go the route of um, burning hydrogen? So it all kind of has agglomerated together to create a large demand in electricity. And of course, the one probably most have heard about is data centers, right? That adds on top of that. So you kind of have the perfect storm of users and demand off takers that need a lot of power and electricity. So it's kind of forced utilities to think through, okay, what energy sources can provide that much power in a quick enough time, in a reasonable enough time frame to match all this burgeoning demand that's coming down the pike. And it has forced a lot of them to conclude that nuclear is a good solution, among others. So why is that? The high capacity factor is one. The predictability, we know how to build them, right? So Westinghouse has built the AP1000s down in Georgia. They've built them in China, about four of them, and we're in the process of building some more in Europe. Now, when we think about the different classes of reactors, you have anything from our large scale reactors, which are our AP1000s, to our SMRs, which are our AP300s, which are about 300 megawatts, and then our microreactors, which are about 5 megawatts. They can range anywhere between 1 to 20 on the spectrum, but our variation is about 5 megawatts. And the reason why we have the different classes of reactors is because they serve different market segments and different applications. So large scale reactors, such as our AP1000, those are generally central power plants providing utility scale power to the grid. SMRs, those are for smaller grids usually, or for applications for direct coupling to maybe industrials, to power, to maybe data centers. So they can be done behind the grid or on the grid. So they kind of live somewhere in between. And finally, you have microreactors. Microreactors are much more niche in their applications. They can be part of decentralized grids or distributed grids. They can serve as a base for what we call virtual power plants or on microgrids, islanded grids. There's been a trend to look at them for military installations where you need highly reliable power, where you don't want to be dependent on the grid. And also marine propulsion. So that's been another demand driver for microreactors. So within that, even as we break them down into, let's say, megawatt or power output scale, there's even within those classes, there's different reactor technologies, right? That are based on their fuel type and their coolant type. So you might hear Gen 3 reactors, Gen 4 reactors. Gen 3 reactors are basically what we have today. The AP1000, what we're building, and those have what we call passive safety systems. So safety systems that would be able to effectively mitigate some kind of accident condition and not require active measures. So if you heat up your reactor, if you have an unanticipated shutdown and for whatever reason you don't have offsite power to power your pumps, the reactor can still cool itself based on physics. So if you think about it, it's what we call natural circulation. You have your reactor getting hotter on one part, and the colder part on the top is more dense, so it pushes the hotter part, which is less dense, and it creates a natural circulation flow, so it has the ability to cool itself. That's not to say that the reactors don't have active measures, they do, but we use passive measures just as a fail-safe. When we look at our Gen 4 reactors, those are reactors that are in development today, that are slated to be on the grid late 2020s, early 2030s, depending on what flavor of reactor you're considering. And they can have alternate coolants. such as molten salts. They can have sodium, so liquid metals or lead. They can have gas, they can be gas cooled, and they all have the different benefits, whether it's higher temperature, better materials, a combination of fuel and coolant that creates additional safety benefits. But at the same time, they all have different risk profiles and trade-offs, right? So when you're considering technology development, whatever flavor you take, you have to kind of bend the risk into different buckets, whether you're talking about regulatory risk. We do live in a heavily regulated environment, where we have to have assurance that our systems will work the way we claim they will, so we don't have unanticipated consequences. Westinghouse is lucky to have a long history in the regulatory space with a licensed design in the AP1000, also experience with that leads directly into the AP300, which is a scaled down version of the AP1000. And finally, we leverage that experience in our microreactor, the eVinci, which is about 5 megawatts. Other risks are supply chain, right? So since you're talking about new technology development, and this is not unique to nuclear, it applies throughout the sphere of hard tech and clean tech. How do you build up supply chains that don't for a product that doesn't yet exist or that's a first of a kind? Again, here we're lucky to have a robust supply chain as a company, so we lean on them, but there are areas where we have to develop either internally or with partners. The next one is you have policy risk, right? Well, you have supportive policy that will be an enabler. Government is always a stakeholder in the nuclear space. So you always want to have a supportive policy environment that enables the adoption of different technologies. And in the US, we've been very blessed. We've had quite supportive bipartisan support, which is great. And then finally, this is a more obvious one, but you also have technology risk, right? How will your technology actually work? Do you actually have the materials? Will it perform the way you think it does on paper or on your design files and your design documents? One way to do that is to test over and over again to make sure that your simulations, your models actually correspond to what's happening in the physical world. So here you have to make a lot of trade-offs, right? If you want to achieve higher temperatures for higher performance, do you have the materials? Yes or no? Or will your materials perform well under corrosive and hard environments? So you have to consider all these things in a blend when you're deciding, well, what reactor should I build if I decide to build one? And then to get to that, to reduce your technology risk, you effectively have to consider what are your enabling technologies. So this is kind of the fun part for the technologists in the audience that kind of care about what are the cool gizmos and gadgets that we're using in the nuclear industry um, to mature our designs, to give a better shot at building faster and cheaper and better, and hopefully all three at the same time. Now, one that comes up a lot is AI. So everybody hears AI, it's a buzzword, but what is actually being done and how do we use AI for nuclear? There are several ways. Um, Westinghouse released a tool called Bertha, which is basically a nuclear-specific AI agent that does natural language processing. You can talk to it. It's almost like a ChatGPT specialized in nuclear. And you can go through it, give it prompts, it will answer. You can rebut what it said or tell it to modify its answer, and it'll um, take that feedback and give you new answers based on well documented and referenced sources. So a good example is with materials. I could ask it, hey, I want to relieve pressure on my fuel rods. What material could I use? And it tells you can use a material, a combination of nickel, chrome, cladding for whatever reason, and it cites why. And you can say, well, I don't have access to a supply chain of readily available nickel or chrome. Then it'll go back and say, well, try modifying it and adding this alloying element instead. We've been lucky because we have a lot of data. We're a 60-year-old company. So we've been able to call all that experience data and feed it into the AI agent, into Bertha. So it has plenty of information to build on. Um, the other nice thing is that we service probably a good chunk, a good fraction of the US fleet. So we have data from operating plants based on what we've serviced. And also, a lot of the designs in the nuclear fleet globally are based on Westinghouse designs. Now, other cool technology, or pixel shovels, as we call them, is we have new fuel designs. So what we call our accident tolerant fuel. What that does is it allows for a greater safety margin, which means we can perform better. We can extend the fuel cycles for our utilities, and they can run their plants more economically or capture greater margin as they're operating in the electricity markets. We've looked at virtual training. So because one of the big gaps is workforce in the nuclear industry, is how do you actually build all these reactors that we're seeing demand for from the market? We have a limited workforce. We've had a hiatus of about 20 to 30 years in building. So that translates to universities haven't been producing enough graduates or craftspeople um, capable of doing nuclear quality welding or doing design work for the nuclear industry. So, are there tools we can use, whether it's through virtual reality and augmented reality, and apply this to our training and onboarding programs at Westinghouse? And finally, these are not unique problems just to the nuclear industry. Other industries have faced this in the past, where they've had gaps in talent or they haven't had enough um, workforce for their growth projections. We've seen that in the aviation industry and the automotive industry. So, are there clever ways we can adopt from other industries or create partnerships with other industries or industrial players that can speed up our own internal development? So, with that, I will wrap up my talking points. I think at about time. And I want to give people the chance to ask questions so we can turn it into a discussion. But with that, I will say the main takeaways is that all energy policy effectively or trade-offs in your energy stack need to be made based on fundamental principles, right? Energy security, your energy availability and growth projections, and your sustainability. And you have to mix those and see what is most valuable and most important. The second thing is there's lots of growth in the nuclear industry. So I know you have a bunch of students that are finishing PhDs or dissertations. The nuclear industry is hiring. We're doing a lot of cool things. So it is a really awesome field and a good time to be joining if you're interested. So with that, I'll turn back to our moderator.
Thank you, Harry, so much. That was very insightful. So I think now we'll go ahead and move into the Q&A portion. So Harry's left us a good amount of time. We have about half an hour for questions. So as a reminder, please submit your questions through the Q&A question portal link that's been sent in the chat by Eliza. I see we already have some questions, so I'll go ahead and begin with the first one. Which is from Bo, I think Harriman. Hopefully, I'm pronouncing your name correctly. Bo asks, if we were to build out large chunks of nuclear energy infrastructure across the US, what are the short-term emissions costs of developing, building, and launching this infrastructure? And when, in your opinion, and based on your knowledge of current carbon costs today, would it net out?
Okay. So if you look at nuclear, its environmental footprint is quite low. It's similar to that of a solar or wind in terms on a per kilowatt hour basis, right? So um, it doesn't change much from the perspective that you need to increase your manufacturing, but that applies to any source, right? Um, the other thing that could come up is the emissions during um, mining, but that again applies to all energy sources. So it's not something you can avoid one way or the other. When we talk about what would the near-term carbon footprint be of increasing nuclear supply. Um, these are common across any energy source. So if you think about the mining question, you have to mine for coal, you have to drill for oil, or frack for gas, or get it from a different energy formation. Same thing for batteries. You need critical minerals that requires mining. And again, same for your renewable sources. So it doesn't really change from that point of view, but you do have to increase your manufacturing capacity for sure to increase your energy infrastructure, your nuclear infrastructure, if you're to have a large scale energy build. But overall, I would look at the life cycle emissions of nuclear, which are comparable to renewables. So they're extremely low.
Thanks, Harry.
And I
Uh,
think there was a part on timeline, if you can remind me. So I didn't want to leave that open.
I think the second part of the question was just like when, based on like the knowledge of the current carbon cost, when would like the nuclear deployment
Net
net?
out,
Yeah.
net out. I mean, again, if I have to go back to the the life cycle emissions, I would say it would actually make it better because you're replacing emitting industries, right? So if you compare what is baseload, what is considered baseload on the grid, you would be replacing either coal or natural gas or something equivalent, which means you'd actually have a much better carbon footprint and impact. And you can see the reverse of this actually when nuclear plants retire, emissions go up.
Mhm.
So New York has had that when they shut down their Indian Point nuclear power plant, their emissions went up immediately because it got replaced by like-to-like energy source, which was natural gas.
And maybe Harry has like a short follow-up to that question. Do you think that like the kind of like that time for like the nuclear infrastructure to net out, does it depend on like where you deploy the nuclear reactors? For example, like if you're trying to mine for uranium or some nuclear fuel in certain locations, for example, I guess it's easier to find that fuel. Is it like supply chain dependent, or is like the kind of like the carbon costs or whatever costs you have from exporting or importing, is that marginal depending on like where you deploy the infrastructure?
I think it's marginal overall, I would say.
Okay.
It's marginal. I mean, it depends again. You might have some effects on the manufacturing side, depending on where you're located, because their manufacturing is energy intensive. So it depends on what energy mix is feeding that manufacturing, right, and that upscaling. But on mining, it's usually done in remote locations, regardless.
Hmm.
And the thing about uranium, uranium a lot of times is not a prime mineral that's being mined. It actually is co-extracted with other metals such as vanadium that are used in different industries.
Right. All right. Very good. Thank you. So let's move to our second question, which is from Lee Swanger, who's a Hertz fellow. Uh, and Lee asks, assuming magnetically contained fusion becomes practical, will escaping neutrons create radioactive species in the materials surrounding the device that will need to be carefully stored before they decay to a safe level?
So I will admit I'm not a fusion expert. I do not have much insight on fusion. What I will say is that is a question for the regulator, right? The regulator is working with fusion companies to start assessing what is the regulatory framework for evaluating nuclear safety cases. So they're going to have to go through the same exact process that the fission side of the house has had to go, right? You have to consider what are your design basis accidents, and how does that effectively translate it to a wider dose to the public, right? So the way the regulator works is they have some standards that are defined as what is your dose to the public after a severe accident or event, and you have to work backwards to prove that um, you have enough mitigating measures. So unfortunately, I can't answer the specific question because it's outside my domain, but it is a question for the regulator.
And maybe Harry, related to that, can you talk a little bit about like whether Westinghouse, like the infrastructure that Westinghouse develops, whether there's some common infrastructure between the nuclear fission and fusion side of things?
To a degree, there is. Westinghouse is involved in limited capacity in the fusion world. So we have manufactured large chunks of ITER's vacuum vessel. Uh, these are massive, massive components of the vacuum chamber. and we have the capability to build those. So, other capabilities that might overlap with fusion is our ability to build plants, or to design plants, actually. If you look at where the fusion companies are today, they're in the stage of designing their fusion machine, but they haven't translated that to what does it look like as a commercial plant. And that is somewhere where Westhouse does have experience and is at a very low level working under funded projects with, I think, one of the fusion companies to do that exact problem.
Okay, cool. So maybe we'll move on to our third question, which is also about fusion, but I think maybe more of an opinion question. So this is from Ben Tannenbaum from Sandia National Lab. And Ben asks, practical fusion has been 20 plus years away for many decades. What happened in recent years to drive so much private funding into fusion energy, which maybe is you don't need to answer, but and do you think we will see fusion generated electricity on the grid in the next 5 years? What will happen to small modular reactors in that case?
Again, being a fusion outsider, I'll give some thoughts. What has driven investment? It's the fact that we've taken an all of the above look to energy. We have significant energy needs, whether it's because of all the growth we have internally, or countries looking to how do they meet their energy targets. So if you think of China, if we go back to the example about how much they consume per capita, and India, if they consume about a tenth of what we consume or a quarter of what we consume, and you multiply it by their populations, which are at this point almost 2.5 billion, that's nearly a tenfold increase over what we have in terms of population. And you multiply that by their per capita growth needs, that means we're going to have to grow the energy demand by 50 to 100 times. Right. So just to frame the scale of the problem and why we're trying everything, including fusion, and we're reconsidering fission, it's just the scale of the problem is enormous. So demand has driven the need to look at all different kinds of technologies. Now, whether they'll be on the grid over the next 5 years, the thought I'll offer is the following: is they have a risk profile to their technology, just like fission does. They have to go through supply chain, they have to go through regulatory policy, technology, and all of those have to be addressed before you have a workable commercial scale power plant. So I can't speak directly to where they are in terms of development or technology readiness or commercial readiness, but they still have the same buckets of growth, risk, and scaling that any other technology has.
Excellent. Very good. So I think our next question is from Daniel Slichter, who's also a Hertz fellow. And Daniel asks, what is new with respect to waste mitigation to address concerns about long-term storage of spent fuel and other radioactive materials?
So I will kind of flip this question around. It might be a bit unconventional, but I think spent fuel is actually one of the biggest assets to nuclear because we've done such a good job of managing it,
Hmm.
right? We account for it. We know exactly where it is. We safely store it, and it sits there just doing nothing effectively on big concrete pads. When you consider what is the waste issue of other energy sources, right? Let's say carbon emissions, those are not controlled, those are not mitigated, those are just spewed out. We don't necessarily track them. So you can kind of see if you flip it, like what is the actual impact of our spent fuel and our waste? You again have to compare it to your other energy sources and when you're making your trades. Having said that, now there is a real issue around public acceptance and public perception of spent fuel and what do you do with it. Um, the original plan in the United States was that the government would take ownership and control of it and put it in a centralized repository out in Nevada. That has unfortunately not happened. So, what are other ways we can do it? Are there innovative business methods, whether you can consolidate the fuel in a single location? Can you use alternates to geological repositories such as boreholes? Or can you even consider recycling the fuel? Um, and these are all, not all of them, but some of these solutions have been implemented abroad, such as recycling in France, or even the repository, consolidating waste in one place. We're seeing Finland is well on its way to opening a centralized repository for its spent fuel. Sweden has taken the same approach, and same in Canada. They're well along their way. But what they've done is they've had local buy-in. They've taken a lot of time to do community engagement and make sure that the host communities are willing to host the spent fuel. And finally, there are any other number of technologies. Again, recycling, that one is one that is really cool that's being done in France. So that's why I said you spent fuel is kind of an asset. We don't know yet whether it truly is a waste or we can repurpose it to extract more energy from it in the future.
I see. And here, can you go into a bit more detail about like what does that recycling process look like for spent fuel?
Okay. So there's two ways to do recycling. One is what we call an aqueous-based method. So that's basically you're taking your fuel, you're kind of cutting it into pieces and then dissolving it in acid and pulling out different streams of what useful and waste materials you have. And usually you're trying to pull out fissile material, which could be uranium, plutonium, or your transuranics, such as your americium. And then you take that material, you feed it back into a fuel fabrication facility, and then reuse that. The reason why you do that is because the current energy content of the fuel, we burn about 5% of it, and we kind of store the rest, the other 95%, without actually putting it to any use. So there's a lot of energy content left in spent fuel. I would call it as lightly used fuel rather than spent fuel.
And are like these current recycling methods like quite energy intensive? Is there like room for innovation on that side to like reduce like the carbon costs of like actually recycling the spent fuel?
Yes, yeah. So there are ways to do that. RPE has a great program under Curie, their Curie program that was looking at that specific topic. How do you make spent nuclear fuel or use nuclear fuel recycling more efficient and cost competitive? So if you go onto their website, you'll see a whole slew of things to that effect.
All right, very good. So let me go ahead and move to the next question, which is from Jim Zavislan from University of Rochester. And Jim asks, what is the carbon balance for the utility scale reactor? And how long does the reactor need to operate to pay back the carbon needed to build and operate it? So this was kind of related to the first question we had, but maybe the first part of the question, Harry, you can chime in on what is the carbon balance for the utility scale reactor?
It's still quite small. It goes back to the original question of what is the life cycle emissions of a nuclear power plant. There have been any number of studies that have been done on this, and one of the biggest, and some studies are a bit outdated. One of the biggest cost drivers was the enrichment carbon footprint. However, that considered what we call gaseous diffusion enrichment, which was extremely energy intensive. And because of what the grid that it's in, it was powered by coal power plants out in Tennessee. So it had an intense carbon footprint. Since then, we've actually moved as an industry to what we call centrifuges, centrifugal enrichment. It's your they look like tall rods. They just spin very quickly and separate uranium 235 from 238. Those are a lot more energy efficient, and they're the industry standard at this point, which reduces your carbon footprint significantly. So I would say again, the answer reflects the first question. My answer to the first question, that it is quite low and on the order of um, whatever other renewable sources have. And because of the long lifetime of reactors, 60 to about 80 years at this point, you can spread those carbon emissions over a really long period. So that is one of the benefits. There are no real emissions during operations. So all of it is upfront emissions, effectively.
Pretty good. And do you have like a rough estimate of the time like it would take to become carbon positive?
Not off the top of my head. Not
Okay.
off the top of my head, but I doubt it would be long, just because of two things, right? Your outputs are really big, right? You're
Mhm.
talking gigawatt scale, 24/7, 365. So you're quickly reducing your carbon emissions just because of your large output.
Makes sense. Okay. So our next question is from Douglas Bowman, who is a Hertz fellow as well. And Douglas asks, while I have been a long-term supporter of nuclear power as part of the solution to meet electrification needs, some total life cycle risks seem to remain. And he asked specifically what new options are available for the spent fuel storage slash disposal problem, including the transportation of nuclear waste. Doesn't this problem need to be worked at the same time as we consider expanding nuclear power globally?
Yes. So um, a lot of the answers are similar to the previous one, the previous question. Um, the one differentiator is the transportation. I will say that transportation, yes, it is being considered actively. There are several transport casks that are being designed by different companies to be able to handle the fuel transport effectively. But at the same time, we've been doing fuel transport for a very long time, right? Whether not necessarily commercially, but we have been doing it at a federal level, taking fuel from our submarines and our aircraft carriers out on the East Coast, all the way across the country to out to Idaho, where their final resting place is. So we have decades of experience in transporting used fuel. And same thing, we have a repository out in now, of course, I'm forgetting the name, but we have a repository for defense waste where we've been doing the same exact process, transporting defense-related waste down to a repository and storing it safely for the past couple of decades at this point.
And is that infrastructure for like transporting nuclear waste established in other countries as well?
Yes, yeah, you have the same process being done with France. They take back fuel from the UK and Japan, so they
Mhm.
take it across continents, bring it, reprocess it, and then ship it back to the originating country. So it is a mature industry. Fuel transport is quite mature. Um, so again, you do have to design, especially with new reactors coming online, new classes of reactors. You do have to design specific to their fuel composition,
Mhm.
but it is an engineering problem in the end.
And does that also enter in like the location in which you would like say you wanted to build a new nuclear reactor somewhere to make sure that it's like close to the infrastructure that you have to transport nuclear waste?
Yeah. So it depends. It doesn't necessarily have to be that way, but if it does make business sense of co-locating,
Hmm.
if you have some economies of scope by doing that, sure, but it's not necessary. It will be a business decision in the end.
All right. Let's see. So our next question is from Charles Tierhart, if I pronounced your name correctly, who is also a Hertz Fellow. And Charles says, you mentioned marine propulsion as an application for microreactors. So can you elaborate on this a little bit? Efforts have been made a few times in the past to transition to nuclear power commercial shipping, going all the way back to the 50s. And what has changed recently to make this application more commercially viable?
So one of the big differentiators, and there's been quite a number of discussions around this in the past, that is true, is the pressure to decarbonize shipping industry. Right? The IMO, so the International Maritime Organization, which is part of the UN, has released decarbonization targets for the industry writ large. We're also seeing in Europe what we're calling carbon adjustment border mechanisms, where they're charging for imported goods based on their carbon intensity, right? So we're seeing basically the pressure to decarbonize forcing shippers to consider alternate sources, whether it's ammonia, whether it's through assisted sails, through um, hydrogen, or some other type of non hydrocarbon, or nuclear. Again, the differentiator with nuclear is that it's um, capital intensive, right? So it does require significant investment upfront, but at the same time, what it does offer as a benefit, it's its energy density, which can increase the speed at which you ship, right? So you have to basically trade your upfront cost versus the increased efficiency in shipping and the longer routes you can take as well, just because you don't need to refuel, right? Nuclear fuel can be designed. You can have reactors that are based for maybe 7 to 8 years that can run nonstop without refueling. Now, there are other questions that are being actively looked at. Well, what is the uh, regulatory landscape for docking nuclear ships, right? That is a real question that's being addressed, and it's not an easy one to address, right? So it does have a lot of promise, but it does have a lot of questions at the same time.
Excellent. And so it seems like the policy pressure is there, to decarbonize the shipping industry. On the technology side, though, like, has the technology fundamentally changed since like the initial efforts to use nuclear powered commercial shipping, or is it mainly like an engineering continuously trying to improve the efficiency?
So there's a bit of a mix of it. So if we look at what's been done in the past, we haven't had really a commercial ship. We've had our aircraft carriers and our submarines, but those are different designs. They might be water cooled, similar to our reactors, but they use highly enriched fuel, which means they have completely different physics, design principles. So you do have to design them for purpose based on civilian constraints, right? What has changed though is we still have different coolants, different fuel types, so that kind of shifts the way you design the ship around it. You also have to consider roll and pitch. What happens if you're on a big wave and then your reactor all of a sudden is vertical rather than horizontal the way it's supposed to be? So there are questions of engineering. There are also questions of materials and technology development. It's a mix of both, I would say.
Okay, excellent. So it looks like we have maybe 7 more minutes, so maybe two more questions or so. So the next question is from Charles Kim, who's with Howard University. And Charles asks, nuclear power plants brought in unintended ill impact to marine ecosystems due to the warmer temperature near the cooling water release pipes. Regarding the SMR, the small modular reactor, what kind of unintended consequences or the unknown unknowns are you prepared to consider?
Yeah. So first off, you when you look at power plants and waste heat, so this is um, you have about 3 gigawatts of from our large scale reactors. It's about 3 gigawatts of thermal power. One of it gets used, two of it gets released and needs cooling. Now, there are different ways to mitigate against that. We're looking at dry cooling technologies, right? How do you cool without the need for water? We believe that is something that's feasible. It does have some kind of cost impact, right? Because you're reducing your performance, but at the same time, you do have some economies from not needing to use all of the equipment that you need for wet cooling, right? The condensers, cooling, some form of cooling tower. So you kind of have a trade between the two. So there are ways to mitigate direct cooling. Now, a funny anecdote I would say is that if you go to Diablo Canyon, they're right on the coast on the Pacific Ocean. Because the water is warmer, you actually have a thriving marine ecosystem. You have a lot of wildlife that actually goes there because it is warmer and more comfortable. Because the Pacific Ocean is cold if anyone has actually put their feet in there. So yeah, there are ways to mitigate against thermal pollution, and we are considering them actively.
Excellent. So our next question is from Paul Pertini, who's with the Electric Power Research Institute. And Paul asks, Amazon, Google, and Meta today call for tripling the roughly 110 gigawatt nuclear generation capacity in the USA by 2025. If this were to occur, how do you see the portfolio mix of new reactors developing? gigawatt scale developments versus small modular aqueous coolant developments versus Gen 4 advanced non-aqueous coolant developments, and over what timescales given capital and safety demonstration requirements?
So I wish I could answer that question with precision. If I could, I would go and bet on the stock market today. But unfortunately, it will depend on applications, right? There definitely will be growth in nuclear, whether it's as big as it's projected versus something smaller. It will really depend on what the real need for power is, what the trade-offs are, and then what the different markets are, right? So, gigawatt scale are great for centralized production at a utility level, but they're not ideal for every situation, right? Smaller countries that have smaller grids, they might not be able to basically afford to put nuclear on their grid. They might need SMRs. And then the second question becomes how mature is the technology and how quickly do you need it, right? So water is a mature technology. We can build it today. We are building it today. We have built it. So you kind of have to determine what your timeline is versus your um, performance levels for Gen 4. Gen 4, the claim is that since they have higher temperatures, better performing fuel, they have reduced safety necessities or requirements, um, or added features, so their cost drops down. But at the same time, they have to prove all the safety case out, right? And prove out their economics through testing. So it depends. The off-taker has their own priorities. It depends on the off-taker's timelines, their willingness for risk, whether that's technology risk, whether that's regulatory risk. So they have to balance that out. And I really wish I had the answer.
And maybe, Harry, if you can, like, so this 110 gigawatt estimate for how much AI will require by 2025, how much do you think that can be obtained just by bringing like offline reactors back online versus building new reactors?
So in the past, I think 10, 15 years, we've taken maybe 10 to 15 reactors offline. That would equate to 10 to 15 gigawatts. If we had magically could bring them all back online, certain of them are in more advanced decommissioning phase, so bringing them back would be a lot harder. Whereas others are in what we call a safe store situation, which is the utility just leaves them as is and has a plan to come to them at some point in the future, maybe 10, 20, 30 years in the future to deal with full on decommissioning. What happens in that case is they remove the fuel and store the fuel, but the reactor just sits. But it's not an easy task to rehabilitate. You still have to think of leaving your car unattended for 5 years. You still have to change its fluids, any gaskets, make sure the tires are okay. So it's the same exact problem, just at a bigger scale with a nuclear reactor.
All right, very good. So we have about 2 minutes left. So with that, since we're nearing the end of the hour, Harry has offered to stay in for another 10 minutes if there's additional questions, and I know there are. But for those who need to leave, I just want to thank Harry again for his really wonderful presentation, and to let you all know that the video recording of this talk will be posted in the next 7 to 10 days and can be shared with others. And just want to plug our next innovation hour, which will be held on May 22nd, with Hertz fellow Ken Brown, who will be talking to us about modern quantum technologies. So please save the date. And I think Elisa, Harry has also offered to share his contact information in the chat. So Elisa will share his email in case you want to contact him. All right. So I guess we can move to the next question, which is from Wendy Chislak from Sandia Lab. And so Wendy asks, your AI example that you presented was greatly simplified, I'm sure, but for materials, there's so much more than the element. There's alloying ratios, processing, microstructure, surface finish, and many other factors. So what would keep a question asker from being misled by the AI?
So that is a fantastic question. The example was indeed very much simplified, but it does provide references of its logic and why it gave you that answer, right? So you can actually go through and ask it, the alloying elements, does surface finish impact my results? It will actually do the analysis and give you the references underneath based on our regulatory documentation. But again, AI is a tool, right? And it depends. It requires user judgment and subject matter expertise, right? So you can't blindly rely on it to say, okay, I'm an undergrad that just came out. I'll have AI design a reactor or pick my materials. It also does require a human in the loop to be effective.
All right. Let's see. So our next question is from Adele Payman, who's a Hertz in-school fellow from Caltech. And Adele asks, what specific measures have other countries taken to improve the public perception and trust in nuclear power? And what do you think would work in the US?
So I can give a couple of examples. In Poland, for example, if you look at the support ratio in Poland, it's about 80%. They have no nuclear. They're trying to build new nuclear, but the government has done an extremely effective job at promoting the reasoning behind it and including the public in the discussions and debate, right? So they've had an open discussion. Um, Another example of where this has been done very efficiently is the UAE, so the United Arab Emirates. They started, I think, in 2008, 2009 with a decree at a government level, but they included the public in every step of the way. They included transparency, they included education programs. So there was a coordinated federal level or government level, state level policy to include the public in the decision making. So I think that is probably one of the biggest keys is making sure you have an informed public. There have been instances where the nuclear industry has been a lot more opaque. It also has been confounded. The civilian nuclear industry has been confounded with a defense nuclear industry. And
Mhm.
those are two separate entities, different purposes. And it's important to make that distinction, right? Because we do have a lot of baggage that comes from the defense industry that gets thrown onto the civilian side as well.
And I guess within the US, since you've been in the nuclear industry, both like in the government and the industry and in the academia side, have you seen in your time like a shift in the government and the public's perception? You mentioned, there's this bipartisan support for nuclear energy development. Has that changed over time?
Yes. So one side of the aisle has traditionally been more pro-nuclear. The other side of the aisle has been more hesitant. But we've seen because of all the things that are happening, whether demand growth, whether energy security issues, competition with China is another big one. Nuclear energy is being used as a geopolitical tool by Russia and China. If you look at Rosatom, they have a $200 billion order book abroad for new reactors, and that's countries that could even be considered allies or at least aligned with the US, such as Turkey, Hungary. They're building Russian reactors. Egypt, they're building Russian reactors. So it has shifted the perception both because of demand growth and energy needs, but also geopolitical competition with our adversaries.
All right. Our next question is from Miguel with the NSHP, and he asks, "What do you think are the reasons for the fear of nuclear energy from the public at large? Do you think that competition of the different energy sectors may have an influence here?"
Um, yes, absolutely right. You have marketing campaigns from all different energy sources. So absolutely right. Everyone wants their horse to win in the race, so they will say one is better than the other. I will say the following: that there's no silver bullet, and you have to pragmatically consider what trades you're willing to make to pick your ideal energy mix. Right? Nuclear is great in certain circumstances, in others, it doesn't make sense. Um, so, with that, first part of the question, remind me again. I didn't.
So the first part was just, what do you think are the reasons for the fear of nuclear
Yeah,
energy?
yeah. So education. It goes back to education. We haven't been as transparent and doing a good job at promoting the positives of nuclear, right? Um, Again, I think like our used fuel is an attribute, and even though it's been presented as a waste or a negative, to me, the fact that we haven't had to act on it, or the fact that we haven't had to really do something and it sits on concrete pads at different utilities shows the innate safety case of the fuel, the used fuel, right? The fact that they've been sitting for 30 years on a pad and nothing has really come from it. Whereas at the same time, we're releasing tons of CO2 into the atmosphere. Um, that to me is a lot more problematic than the fuel sitting on a pad. And the other thing that's interesting about the fuel is that it's tiny, right? We're talking about the entire generating fleet of the US over its entire lifetime. You can fit all the used fuel on a football field 10 feet high or 10 yards high, but it's not big, right? If you do the same exact problem with gas or let's say with coal or with the debris from renewable sources, you'll have orders of magnitude more
Mm.
waste you have to consider. So I think one of it is public education for sure. And the other one is we haven't been able to create, let's say, an appealing marketing campaign as a nuclear industry. You think about BP, they do a very good job of marketing renewables. I remember going through Dulles Airport, which is my local airport, and going through this long, I guess it's not an escalator, but a walkway, mobilized walkway. And it's ads from BP saying we're all about renewables. Meanwhile, that's a percent, less than a tenth of a percent of their spend.
Mhm.
So yeah, marketing is important, and public education I think is important, and also the confounding the military history of nuclear with the civilian nuclear that has also been quite tough for the industry.
Very good. Okay, so our next question is from Mark Cronshaw, who's also a Hertz fellow, and he asked, "What is different about how the French handle spent fuel?"
So they recycle their fuel. They are looking at repositories, so putting an ultimate repository as well, and essentially placing their spent fuel deep underground in isolation. But at the same time, they're also doing the recycling part, and it's twofold, right? Recycling can have both civilian and defense applications, so it's a dual use technology. The question is, how do you design so it's not dual use? And there are ways to do it by what you decide to extract, right? Do you extract pure plutonium, or do you want to extract um, plutonium metal mixed with other transuranic elements, so americium? If you do that, then it doesn't become weapons usable, and you can control the dual nature of the technology. France, again, their utility is publicly or state owned, partially state owned. So they can afford the economics of it effectively, and they have dual intent with using their facilities.
Very good. All right. So I think it's time for our last question. We just have a couple minutes. So the last question is from Miguel again from NSHP, and he asks, "Who is producing the most developments in nuclear energy? Is it the public or private research, and which countries as well?"
I think the innovation landscape in the U.S. is quite robust. We have about, if you look at, there's a Third Way report. Third Way is a think tank out in DC. They did a report of all the new startups in the nuclear space, and I think last count was about 70 or 80 new startups. Right, so that tells you how robust the innovation ecosystem is. Um, what's happening in China, however, is they have less technology spread, but a lot more resources dedicated to development.
Mhm.
So there's a paper that was released by another I think think tank out in DC that said that we're about 10 to 15 years behind China in terms of nuclear. The reason being because they're actually building all the Gen 4 technologies that we're trying to develop in the US because they throw resources and they manage to pick a topic and go after it, right? And we're seeing that not just across for nuclear, but we're seeing it for fusion, we're seeing it for AI, we're seeing it for chip manufacturing, we're seeing it across all industrial landscape.
All
So
right.
I would say the US is well advanced in terms of breadth of technologies. China is more advanced in actually like building and deploying. And
Excellent. All
Europe
right.
is
I think
Europe is somewhere in between. They have a less robust ecosystem, but we're seeing it develop there as well, in fairness. So there are European startups, companies that are and established companies that are considering new technology. And again, it depends whether it's publicly or privately funded. It's a mix, right? So a lot of the startups are privately funded. There's a lot of private capital, but you do need support from the government, right? Government's still a stakeholder. They do provide non-dilutive capital for R&D, for basic questions that are cross-cutting across the industry. So government absolutely has a place and a stake in technology development and maturation of the industry.
well, it's certainly an exciting time for nuclear, and if maybe in a sentence or two, maybe Harry, you could share with us what are you most excited about right now in the nuclear industry?
What I'm most excited about is honestly the amount of growth that's projected. Obviously, I can't say really what's happening behind closed doors, but there is a lot of demand. There's a lot of demand. As Westcast, we're getting pulled left and right to look at how we could deploy our reactors multiples at a time. And that then leads to what new and cutting edge technologies can we bring that to fruition, right? Whether it's virtual trainings, whether it's AI, what tools can we use to make ourselves more efficient to deploy and meet the demand signal? So to me, that is an extremely, extremely exciting time, both for engineers, business development people, people that like reading through regulations, or even communications experts, right? We have a real need for communications expert, policy people. So to me, it's a multidisciplinary field that needs all kinds of expertise.